like to look at here today is the question, why do we use the sum of the squares of the residuals when we do what's called the least squares linear regression? Why is it more popular to use say the sum of the error and minimize that? And this question first came to my mind, and perhaps to yours, when I took a beginning statistics course many years ago, and when we asked our instructor why we use the squares instead of just the distances between our data point and our the y-coordinate of our data point and the y-coordinate of our regression, he said, well, you square it to make them positive. And then we said, well, why don't we use absolute values of the errors? And he said that would be much too difficult to derive an equation. And he actually derived the equation for the least square regression for us. And since we'd had a little bit of calculus, that was a pretty easy derivation to understand. And as technology improved, I began to wonder why we didn't change over, because we really didn't need such a simple equation. We could do it by approximate methods if we wanted to minimize the error. And a number of years ago, I saw a presentation by Rick Paris, who's a math teacher at Phillips Exeter Academy, and I got his handout and looked at it, didn't fully understand it, but a few days ago I went back and looked at it, and I realized that if I looked at it in a slightly different way, it would be easier for me to understand. So I'm basically taking what Rick said and giving it a slightly different twist. So let's go on to this. Let's start with 3 points. Any 3 points in our xy plane here, I've got A, B, and C. For convenience, I've made their coordinates integers rather. So A is 1, 1, B is 2, 4, C is 5, 5. What I would like to do is do a regression on this. I'm going to keep it simple, so I'm just going to let my regression function be y equals mx. We'll let b equals 0, so there'll only be one parameter to worry about. We won't lose any generalization if we do this. So I've got a little slider bar for my equation, and as you can see, I can approximate my the line that runs through these points. Actually, not through the points, but the best fit line. And so there's a pretty good fit. Here's a pretty bad fit. Just by changing m, I can do that, of course. Nothing new there. What I would like to do now, though, is make 3 new points. And my 3 new points, well, the first one is going to come from the x-coordinates of these 3 points. And I'm going to call it big X. And here it is over here. It's a point. And it's a 3-dimensional point. It has the 3 numbers in it, 1, 2, and 5, which are, in order, the x-coordinates of my 3 data points. I'm also going to define another another point, big Y, and that's going to be the y-coordinates of my 3 data points, 1, 2, 5. 1, 4, 5. So I've got x and y. X essentially is mapped to y by in the data. And there's a third point that I want to make, a 3-dimensional point. And I'll call it YR for Y regression. I'm going to take the y-coordinates above each of these data points, the y-coordinates on my regression line that I'm guessing, and they turn out to be, in this case, 2.3, 4.6, and 11.5. And I think it's obvious that the one way of looking at what's wrong with my graph and why it isn't the best fit line is y and yr are nowhere near the same. If this was a perfect fit, they would be the same. The closer y gets to yr, the better that is, the better my fit is. So what do I mean by the closest y gets to yr? Well, since I've defined those as points, I can actually look at this graphically. So let's take a 3D view. So here's my three-dimensional view of what I've just done. And you can see y and yr are not particularly close together in this three-dimensional depiction of what's going on. And so if I wanted to do my regression visually, what I could do, I could come over here to m and change the value of m and try to get yr as close as possible to y. And you can see as m moves along, it gets closer, then it gets further away, and somewhere in this region right about there, I'm getting pretty darn close. And what I want to do is look at how that distance gets closer. And so we should actually be able to see that. Let's see. See right up here, 3.3 is the distance. And I can make it smaller by changing my slope. Watch over here on the right, you can see it closer. And the distance gets less and less, gets down to 2.87. It just keeps getting smaller. 2.4, 2.3, 2.1. Oh, it's going to get less than 2. 1.9. And even though it looks like it's getting further away there, it's not, because we're looking at this in 3 dimension and we're not getting the right angle on it. So it gets down as low as, looks like 1.87. And when I square that, I get 3.51, because we're used to squaring this sort of stuff. But we didn't find each individual difference there. So what did we actually do? Well, we found a distance. And the way you find a distance is with, of course, the distance formula. And the distance formula, as you probably remember, looks like this. Okay, there we have 2 points, and we've got the associated distance formula, which of course is just the Pythagorean theorem in disguise. Well, in 3 dimensions, it's essentially the formula of the same form. We're just adding that third coordinate, z, and so we just copy over our original 2-dimensional distance formula, and we add in the z term. And that gives us a distance, and we were interested in the distance between yr and y, so we would use that formula. So my distance is going to be the square root of the sum of all of the y. Let's use a big Y. It's the sum of all my yi's minus yr's squared, because of course that's what those are. With my points big Y and big YR. And if I want to minimize this distance, I'm really just minimizing this thing right here. So out of the distance formula comes the sum of the squares of the residuals. And my criteria for what is the best fit comes from thinking of these 2 points, y and yr, as being a good representation of the y data. And so I want to minimize that distance. When I minimize that distance, I minimize the sum of the squares of the residuals, and that's pretty much all there is to it. So given that that's our criterion for best fit, and it seems to me to be a pretty good criterion, and a logical criterion, we've now shown why we use the least squares method for regression. And just to see how close we can come to this, let's show the regression line. and we'll try to stop this m when it gets close to it. Ooh, not close enough. Let's pull it over there. As you can see, when it gets pretty close to it, I can get a fit that has my distance squared to be about 3.47. And if I show my regression line, I can see that with the actual regression line, my error is 3.47. And all I did here was calculate this distance here, and got it squared and got 3.47, which agrees with the result I get from having the computer do a linear regression, having the program do a linear regression. So that's my take on why we use the least squares method. Basically, it's because what we're doing is minimizing a distance between 2 points. Now you say, wait a minute, why did you use 3 points? What if you use 4? You can't see it. Well, we can think of a distance in 4 dimensions. We think of the distance formula as just another extension of the original Pythagorean theorem distance formula. So I'm getting away with calling these things points. If I wanted to make it easier to justify doing this, I might refer to them as vectors. And I might say that what we want is for the vectors y and yr to get as close as possible to each other. So there it is. I hope you find this useful and maybe even a little bit enlightening.